We're going to focus now on trials that have success and failure as the only possible outcomes. The answer is yes or no to a question. For example, is this randomly selected voter going to vote for this proposition? Yes or no? Does this person have an annual income of over $50,000? Yes or no? Is this a gamble I won or did I lose? Yes or no? So success-failure trials crop up a lot, and understanding them is central to understanding what happens in more general situations. So we'll start with them, and we'll start with 3 rolls of a die, and I'm going to count the number of 6s. Now you know, of course, that the die can land 1, 2, 3, 4, 5 or 6. I'm not interested in all that detail. I just want to know, did it land 6 or not? And how many times did it land 6? And so for this problem, it is convenient for me to define success as 6, which even more conveniently, both of those words start with S, so I'm going to call it S. Failure is not a 6. And the variable that I'm looking at is a random variable because its outcome depends on chance, and that is the number of 6s. It can be any one of 0, 1, 2, 3. Which of these it is depends on Taiki's mood. She determines which it is, and hence is not just a variable, it's a random variable. We are interested in the probabilities with which it takes on these different values. So how are we going to get at them? Well, let's see, we've got 3 rolls of a die. I think we can just write out all the outcomes. Just organize ourselves. And we're going to do it this way. Take the outcome no 6s. How can that happen? Well, that can only happen if you have failure, failure, failure. No success at all. You have 3 trials. All 3 have to be failures. What's the chance of that? Not a 6 and not a 6 and not a 6, 5, 6 cubed. You're using the fact that the trials are independent, and so the chance that you have a non-6 coming up is 5, 6, regardless of what has happened before. Is there any other way you can get no 6s? I don't think so. In 3 trials, the only way to get no successes is to have all failures. And so the chance of 0 6s is 5, 6 cubed. That is just under 58%. So you can play the same game when you want 1 6 in the 3 rolls. So that could happen, for example, as success, failure, failure, the chance of which is a 6th times 5 6 squared. Are we done? Even with 1 success? And no, because it could happen in another way, could it not? It could be failure, success, failure. In fact, there are 2 other ways it could happen. What's interesting is that each of these different patterns has the same chance, because here the chance is 5 6 times 1 6 times 5 6. That is still 1 factor of 1 6 and 2 factors of 5 6. Same here. So what is the chance that you end up with 1 6 in your 3 rolls? Well, you can have either this pattern or this pattern or this one. They're all mutually exclusive. So you add these 3 chances. They happen all to be the same. So your overall chance of getting 1 6 is 3. That's the number of patterns times the individual chance of each of them. And you have just under 35%. And now you're experts. If you can find the chance of 1 6, you can do this again to find the chance of 2, and now you have success, success, failure, etc. 2 factors of a 6th, 1 factor of 5 6. Notice, chance of success to the power number of successes. Chance of failure to the power 1 number of failures. Once again, you have 3 patterns that give you the number of successes that you want, and each of them has the same chance. And so your answer is number of patterns times equal individual chance, and that comes out to be just about 7%. So are we done? Well, let's take a look. This is about 35%, just under 35%, just under 7%. So overall, just under 42%. And what about this? Just under 58. If you add 58 and 42, what do you get? You get 100. So we're awfully close to 100% here. We're not quite at 100 because, of course, you could get 3 sixes. Now, if you roll a die 3 times, are you really counting on getting 3 sixes? No, that's pretty unlikely. But it's possible. You can get 3 sixes in a row, and the chance of that is 1/6 cubed, a 6 and a 6 and a 6, and that is 0.4%. If you add these 4 numbers, you should get 100%, up to rounding. And so that 100% probability, that total probability, has been distributed across these possible values. And so you have your first probability distribution. It's the probability distribution of the number of successes in 3 independent success-failure trials, each of which is a success with chance 1/6. You've seen data distributions in Stat 2.1x, lots and lots of them. This is a distribution of probabilities, arrived at mathematically. The possible values by a mathematical consideration, and the proportions or probabilities by a related mathematical consideration. Now, data histograms, what did we do with them? Well, the first thing we did was we drew a picture. And we are going to do exactly the same here using your wonderful online textbook. So here is the distribution that we just calculated. What I'm going to do is first point out the horizontal axis 0, 1, 2, and 3. These were the possible numbers of sixes you could get in 3 rolls of a die. This area here is the just under 58% that we calculated. This is just under 35%. This is about 7, and this is, well, very little. And the histogram has been drawn by using one of the tools in your textbook. It's the number of successes, as we had said, in n independent trials. N is 3, that each have the same probability p, that is 1/6, and it gives me 3 decimal places. So 1/6 is the chance of success on each trial. This distribution has a name. I'll come to that later. For now, what I want you to do is to just look at the shape of it. In 3 rolls of a die, the most likely number of sixes is 0. Some of you will remember that when we drew histograms, I had said that when you have a discrete distribution, such as this integer valued one, 0, 1, 2, 3, you draw the bars centered over the values. That's what's going on here. I'm not saying that there is minus 0.2 of a 6 or 0.3 of a 6. There is actually no action in most of the bar. The action is all here in the center. But there is a reason for drawing the histograms like this, which you are very, very close to understanding now. For now, just bear with me. It's a discrete histogram. The bars are centered over the values. What I'm going to do now is I am going to increase the number of rolls and look at the number of sixes. In principle, we have a program for working out all their different probabilities. And so, for example, if I change the number of rolls to 7, or actually, why don't I change it to 9? And I hit return, look what happens. In 9 rolls of a die, you can get 0, 1, 2, 3, 4, etc. up to 9 sixes. And now the chances are still skewed, but not as skewed as they were before. And of course, the bars are narrower because you're using the same space for more possible values here. Shall we try more? Why don't we try more? 60 rolls of a die. How many sixes are we going to get? Shall we take a look? Aha! 60 rolls of a die, you can get anywhere between 0 and 66. The most easily understood number is 10, a sixth of 60. And look, where your histogram is centered. It's just at around 10. And what is the shape of this thing? Ah, yes, you remember this from 2.1x. This is looking very approximately normal indeed. This is all to come. But this, that we are going to put a curve over it, and indeed you've got a button here that does just that. I'm just going to do this. If I can, there it goes. This, that the peak of the normal curve should be at the natural peak of this histogram, is the fundamental reason for centering the bars over the values. But that is a long digression from where we are supposed to be at this stage. We're looking far too far ahead. We are only at 3 rolls of a die, and this is most definitely not normal. We are going to hide this normal curve because it's a disgrace. Alright, so how did we arrive at these probabilities? By writing out the outcomes longhand. Now, even with 7 rolls, you'd really rather not do that, if you could possibly help it, so let's develop a little bit of technique. So we can roll 9 times and look at the chance of 2 6s. And before we do any calculation, let's get a sense of, is this going to be a big number, a small number, what? Well, in 6 rolls of a die, you wouldn't be surprised to see 1 6, right? Because a sixth of the time, roughly, you see any given face. So in 9 rolls, you wouldn't be surprised to see 1. By about 12 rolls, you probably wouldn't be surprised to see 2. 9 rolls, well, you think that 2 will be hugely likely, but also it won't be terribly small. You expect to see some probability, though not very large. Well, okay, so what do you expect to see? 2 6s in 9 rolls. So what are the other 7 then? Well, non-6s. So I have 2 S's and 7 F's. The pattern has to contain 2 S's and 7 F's, but in any order. And I really, really, really don't want to have to write out all those orders if I can help it. What I know and makes me happy is that no matter which order I write them in, the chance of that order is going to be the same, because it will have 2 factors of a sixth and 7 factors of 5/6, regardless of which order these letters are written in. And so the overall chance of getting 2 6s in 9 rolls is going to be this individual chance of any pattern times the number of patterns. So what we're left to do is to find this, the number of patterns that consist of 2 S's and 7 F's. That is the number of ways of writing 2 S's and 7 F's in any order at all. Well, so how do you go about doing that? Well, you've got to write out your 9 places. 1, 2, 3, 4. There are 9 places here. And in 2 of those places, you have to put down the letter S. This is one choice. You chose place 1 and 2. But you could have chosen place 1 and place 9. You could have chosen these 2. You could have chosen that one and that one. You could have chosen any 2 places out of the 9. And the number of patterns you could make is the same as the number of ways you could choose 2 places out of 9. And what is the number of ways of choosing 2 objects out of 9 objects? That is called 9 choose 2, and numerically it is 9 factorial divided by 2 factorial times 7 factorial, and in our context it is number of trials factorial divided by number of successes factorial and failures factorial. I'll remind you that factorial means 9 times 8 times 7 times 6, etc., down to 1. So what is this number? Well, let's see. The numerator is 9, 8, 7, 6, etc., all of those. In the denominator, you're saying 7, 6, 5, 4, 3, 2. So all of that cancels. And you're left in the numerator with 9 times 8, and in the denominator with 2 times 1. So that's 9 times 8 divided by 2, that's 9 times 4, that's 36. What's the meaning of the 36? The 36 means that you have 36 distinct ways of writing 2 S's and 7 F's in a row. And we are devoutly grateful to this formula for sparing us the labor of writing out all of those 36 ways. In terms of the probability that we were trying to find, we now have it. It's this common chance of each of the patterns times the number of patterns. 36 times the common chance of each pattern. That's about 28%. I've written it out longhand here because that's how the formula looks like when you look in textbooks and so on. Number of trials, choose number of successes. Chance of success to the power number of successes. Chance of failure to the power number of failures. Equivalently, trials factorial divided by successes factorial times failures factorial, and then chance of success to the power number of successes, chance of failure to the power number of failures. Independence is important because of these powers. The fractions remain constant no matter what has gone before. So let's look at the number. It is about 28%, and we had said in the beginning that this probability is not going to be very high, but it is going to be noticeable. It's not going to be tiny either, and that's more or less what you're seeing there. So let's generalize what we have got. It's one of the great formulas of probability theory. It's the binomial formula, and it has to do with the following set of assumptions to which it's a great idea to pay attention. You have n, that's notation, for the number of trials, not any old trials, independent success-failure trials. Moreover, these are such important trials that they are named after the mathematician or mathematicians who first started thinking in these terms, or started at least explicitly thinking in these terms, and these are the Bernoulli brothers. Jacob Bernoulli, I believe, is the one that the Bernoulli trials are named after, though Johann was no slouch either. These were Swiss mathematicians, started out working beautifully together and ended up hating each other's guts. It's very sad. Well, anyway, you have n independent 1-0 trials, and they are repeated trials in the sense that the chance of success on any single trial is the same number p. So the chance that the third trial is a success is exactly the same as the chance that the 7th trial is a success, and we're calling them all p. P for probability, of course. So what does the formula give you? The formula gives you the chance of exactly k successes in these n trials. Now, if you have n trials, how many successes can you possibly have? The smallest number of successes is 0, and the largest is n. So you are looking at the chance of getting exactly k successes for k in the range 0, 1, 2, 3, 4 up to n. And what is that chance? It's what we just found. Number of trials, choose number of successes. Chance of success to the power number of successes. Chance of failure to the power number of failures. And here is the number of patterns written out in factorial notation. That's the binomial formula for the chance of so many successes in so many repeated independent trials. You know, it's a good idea to check edge cases because you've got a k equals 0 here, and that's putting a 0 down here, and that freaks people out. Equally, when k is equal to n, then n minus n is a 0, and that's terribly unsettling until you realize that it's not actually 0, it's 0 factorial that we're putting down here. So why don't we look at the case when k is 0? So you're looking, k is 0, so you want no successes at all. If I blindly, like an automaton, plug into this formula, I'm perfectly free to do that. Let's do it. N factorial, 0 factorial, n minus 0 factorial, so that's n factorial. P to the power 0, 1 minus p to the power n minus 0, so it's 1 minus p to the n. All right, so let's take a look at this. 1 minus p to the n is just what it is. It's right here. P to the 0? Yep, that's 1. Real number to the power 0 is 1. N factorial and n factorial nicely cancel, and you've got a 1 over 0 factorial. What is 0 factorial? Yeah, by definition, it's 1. And can anybody think of why, by definition, it's 1? I believe the reason is to make this formula work out. The number of ways you can choose nothing out of n elements is to do nothing, and there's exactly one way. So, this is all smoke. This whole thing is 1. The n factorials cancel. This is 1. This is 1. And so all you're left with is chance of failure to the power number of trials. And what does that mean? That means failure, 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 failure. Every single trial had to be a failure. Well, yeah, that is the only way you are going to get no successes. So that is, the formula gives exactly the right answer in this situation, and there's our edX checkmark. So what we're going to do now is to use this in an example and connect it to sampling with replacement, which is what your random number generator does. It draws at random with replacement from the 10 digits. And so therefore the trials, the draws, are independent trials. You're drawing always from the same box. It doesn't matter what you've seen before. And suppose I ask the question, run the generator 20 times and find the chance that the digit 0 appears 1 time. By the way, when I say once, that's 1 time, exactly 1 time. Not at least, not at most, exactly. So here I have 20 independent repeated trials, and I only care whether it's 0 or not. So this is a natural success-failure situation where 0 should be defined as success. And so you have the binomial situation. Number of trials is 20. These are independent repeated trials. Success is getting a 0, so the chance of success on any trial is 1/10. How many successes do you want out of your 20? You want 1 success. That's your K. Plug into formula. Trials, choose successes. Probability of success to the power number of successes. Probability of failure to the power number of failures. About 27%. A little variation on this. Find the chance that 0 appears at most once. Well, of course, we're still in the same binomial setting. N is 20, P is still 0.1. We're still looking at zeros. But now K is not just 1. It's 0 or 1. At most 1 means it can be 1, it can be less, but it can't be more. The only way the number of successes can be fewer than 1 is if it's 0. So now I have 2 possibilities for K, which are, of course, mutually exclusive. If something's 0, it's not 1. So what do? I work out the 2 terms corresponding to K0 and K1, and then add them up. The term corresponding to K equals 0, the term corresponding to K equals 1, which you already have, and add up, and you have just under 40%. And while we're about it, let's find the chance that 0 appears more than once. Now, if you just want to do this method here like an automaton, then you have your same old binomial. And now K is more than 1. So that's 2, 3, 4, 5, 6, etc., 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 up to the number of trials, that is 20. So you could do it this way. You could find each and every one of these terms and add them up. Or you could get really, really tired and say, you know what, there's got to be a better way. Which k's are left over? The only k's that are left over are 0 and 1. We already know the chance of 0 or 1. And what we've observed is that more than once is the complement of at most once. This one's easy. Easy or not, we already found it. So the answer we want is best obtained by saying it's 1 minus the answer to something we already did. And that's about 61%. And the moral of that story is don't forget your old rules. Just because you have a formula, you don't have to use it. However, I mean, if I had been in a bad temper and asked you to find the chance that you got, say, oh, I don't know, 6 to 12 successes, then that would be 6, 7, 8, 9, 10, 11, 12, and you know, that's a lot of terms to add, but what's left over is long also. And what if you just had to add a bunch of terms? Well, then of course you need a large size calculator, or you need your wonderful online textbook. So here's a page from your textbook. It's not a page you've seen before, but the general layout will look familiar. How do you find it? I'll show you in a moment off the menu, but what it is a probability calculator. And we're calculating probabilities, so it's quite handy. How do you find it? Well, you will recall that this menu button is always visible to you no matter what page you're looking at, and so you go to Menu and you go to Tools and Demos, which is where you went to find your normal curve applet. This top one here, the binomial histogram, is what I used to draw that blue histogram of probabilities for the number of sixes in 3 rolls of a die. But what we're using now, this page, is down here. It is the probability calculator. You are very familiar with normal probabilities. What we're using now is the probability calculator. It does more than just the binomial, but it starts with the binomial, which is where we are starting, and everything is set to 0. Let's just recall the problem that we were working on. We had 20 runs of a random number generator that was picking at random with replacement from the digits 0 through 9, and we were counting the number of zeros. And so, as we had said, the probabilities for the number of zeros came from the binomial formula with the number of trials n equals 20. So let's go ahead and do that. P is the chance of getting 0 on any particular trial. That's 1/10. So let's go and do that. X is the variable that you're looking at, and the variable is the number of zeros. How many zeros in the 20 trials? And we were asking, you know, what is the chance that the number of zeros is 1? What is the chance that it's at most 1? And so on. So let's take a look at this. What is the chance that X, the number of zeros in my 20 runs, is 1? Well, what am I allowed to do here? I'm allowed to put in X greater than or equal to something, and I'm allowed to put in X less than or equal to something. How do I get X equal to something? Well, the only number that falls into X greater than or equal to 1, as well as X less than or equal to 1, is 1. And the chance is 27%, which is what we had calculated ourselves by cranking out the binomial formula. Ignore these two for now. Patience in a little while. So, this is a little more pleasant than plugging in factorials and powers. And it's certainly more pleasant when you have more than one value that you want to look at. So, for example, our next problem said, what is the chance that the number of zeros is at most 1? So at most 1 means it has to be less than or equal to 1. So why don't we eliminate this, and we just have X is less than or equal to 1. That is, the number of zeros is either 0 or 1. That's the chance of at most 1 zeros, and what we got? Our 39.1%, which is exactly what we had got, longhand. We had calculated the chance of 0, we had calculated the chance of 1, and we had added them together, and we got 39.1. I'm going to take this one off as well. And let's think about the last problem. The last problem said, what is the chance that the number of zeros was more than 1? So take a moment to think about what you would enter here. Yep, certainly you would go for this. More than 1 means greater than or equal to what? 2, exactly. So more than 1 means 2, 3, 4, 5, and therefore greater than or equal to 2. So that becomes a 2, and now you have to make sure that that's checked. And you have just about 60, we had said 60.83% longhand, and that's pretty much exactly right. So you're going to find this tool very useful for actually getting that final decimal answer. The ingredients, of course, you have to sort out by looking at the particular assumptions of the problem. The key ingredients to look for are independent trials. So we had draws with replacement. A fixed and known number of trials. We had 20. Each trial success failure, the chance of success is the same on each trial, and in our case it was repeated trials, and the success was always defined as the trial coming up 0. So the chance of success is 1/10. And the probabilities you're looking for are for how many successes you can get. And that was the variable, the number of zeros in your sample. And then what was left was to find what we were calling K, which values of the number of successes were appropriate for your event, and that's always going to fall in some range. And we've just gone over working out how to use those ranges.